So we had a talk a little while ago from another astrophysicist, Chanda Prescott-Weinstein, who's
nice.
And who. Oh, she's great, isn't she? And anyway, so her work's on dark matter, and she sort of suggested that actually dark matter's a kind of rubbish name because actually it's not dark; it's just kind of more invisible than it is dark. She said actually maybe we should actually think of a change of name because so many people when they hear that term expect it to be like lumps of black stuff, but actually it's not. And so similarly, you said that. Black holes are amongst the brightest objects in the universe. So Kin Yang asks, do you think black holes should have a change of name?
I wish they could almost. I think it would help challenge a lot of people's misconceptions if we could. The dark matter one is interesting because dark matter actually was just a bad translation from French. So pardon my French, everyone, because I'm probably going to absolutely butcher this, but it was supposed to be matière obscurée. So like obscured matter. So like you're saying, invisible matter. Black hole, though, I think is one of those things that was dubbed in English. And I almost think would like White Mountain be like a better description of what it is? Because you just have so much mass all piled up in one place, right? But we think of them as a whole because we think of, gravity, Einstein's theory of general relativity, bending space-time and sinking stuff into a hole. But yeah, white, because they're some of the brightest objects in the universe as well. So I think if we could, we should change the name of a black hole. I don't think White Mountains is quite perfect. Maybe in the chat you can put your own ideas for what you'd rename a black hole. Not Henry the Hoover, we know that much.
Do you think we should name them after a famous scientist like Hawking holes or Hawking objects or something like that? Because there's Hawking radiation.
There is Hawking radiation, yeah. Hawking radiation is hypothetical still as well. So maybe it would be nice for Stephen to have some sort of real object that we've discovered named after him. Yeah.
Fantastic. Tricia asks a question, which is how are the mass of the supermassive black holes calculated? Because you can't just go out there with some scales and weigh these objects. So how do we know the weight and the mass of all these things that are flying around?
Yeah, so as I said in my talk, the way that I did it was with the hydrogen gas that was spiraling around them. So, the stuff coming towards you, stuff coming away to you, this Doppler shift. We also did it in the center of our Milky Way as well, with the actual stars moving around the center of the black hole. So there's lots of different ways that you can do it. There's also different clever ways of doing it, but usually it relies on something moving around the black hole.
And Evailo, I think I'm pronouncing that correctly, asks, obviously we have the huge black hole at the center of our galaxy, but how are they? Do we have other black holes near us? Are there any sort of floating near our solar system, or how are they distributed sort of throughout the Milky Way?
They're distributed just like stars are, to be honest, because it's the stars that form the smaller black holes. So there's no other supermassive black hole in the Milky Way that we know of anyway. But there are these, what we call stellar mass black holes, the things that are about the same mass as stars, somewhere from 3 to 100 times the mass of the sun-ish. 3 is a bit of a contest about where that lower limit is, 3, 4, 5 maybe. So they're scattered around. In fact, just was it last month or 2 weeks ago? I can't remember. It was end of April, early May. But there was a research study that came out that claimed to have found the nearest black hole, or at least a candidate for the new nearest black hole, which was found in the constellation of Monoceros, which is supposed to be a unicorn. So they dubbed it the unicorn black hole, which I quite like. And that's fairly close by, not that close by, there's still a few light years away, I think it was. Can't remember off the top of my head. But the idea that I absolutely love is that there's actually a black hole in the solar system that's about 5 to 10 times the mass of Earth. And which would mean it's about the size of a large grapefruit, sort of like it's about 10 centimeters across or so, which would be incredible. It's this whole thing about, is there a planet beyond Neptune? And I know there's probably some purists out there, they go, Pluto, not Pluto, because Pluto's too small, but something that's actually perturbing Uranus's orbit, Neptune's orbit, and that's also shepherding a lot of the smaller bodies that are out beyond the orbit of Neptune. So Pluto, Sedna, a lot of the asteroids that are out there as well, like the one that New Horizons flew past a couple of years ago. They've all sort of got strange orbits that we can't explain unless there's some other larger planet out there that we haven't found yet. And because we haven't found it, people have been like, well, what if it's a black hole? And I'm like, yes, I'm 100% on board with this idea that the solar system could have its own little pet black hole that's the size of a grapefruit. I enjoy that immensely.
Fun enough, somebody actually asked that in the question. There's a question I was going to come on to. So apart from your obvious, black hole love aside, I mean, what would you say? Do you think that's a good theory, a likely theory? Where would you put the sort of likelihood of there being a black hole, much as you want it to be true?
Yeah, I actually think it's. I remember reading the statistics on it. It's actually more likely that you could capture a black hole than a planet. So we don't think this is necessarily formed in our own solar system. It's probably like glanced past the solar system and been captured by the sun's gravity. And that would be true of like what we call a rogue planet, which I love that phrase. It makes them sound like pirates, just like rogue around the galaxy, right? That have been in some planet system formation around a star. It's maybe encountered another object and it's sort of been slingshotted out of that system and it's roamed interstellar space until perhaps being captured by the sun. That likelihood of that happening increases if it's a black hole, which to me kind of makes it seem more likely. There's also some unexplained things that a survey that's looking for lensed objects has found. So this is when something very dense passes in front of a star and it can act as a lens to focus the light and make it just flare brighter for a little bit. And it's found sort of like 4 that it can't quite explain that could be, if it was a black hole in the solar system sort of passing in front of a few stars in the background. So I think it's quite likely. I am more convinced that it could be a black hole than there's a planet out there, maybe I should say. But I think it's just because I'm obsessed with black holes that I just really want it to be a black hole. So only time will tell. Science, I'm sure, will eventually give us an answer to that one.
And how will we know? I mean, I know we've sent the Voyager probes and now just going out of the solar system. Do you think they might be able to tell us, or do you think the James Webb telescope might tell us? Like, what's the best way to find out?
So Voyager won't tell us. Space is big. You just won't believe how mind-bogglingly space is. I feel like I needed to get that phrase in on Towel Day. But Voyager won't tell us because Voyager, Voyager 1 is going off in one direction, Voyager 2 is going off in another direction. It's very, very unlikely that they'll happen across this thing. James Webb, definitely, because if there is a planet out there and we haven't detected it yet because it's quite far away or it's quite faint, then James Webb should be able to detect its infrared signature, because obviously the way we spot planets and asteroids is we see reflected light from the sun back at us. This is that far away. There's obviously the sort of light from the sun is dropping off by that point. So there's not a lot to then reflect back to us as well. But the infrared light from its just internal heat we could detect with the James Webb Space Telescope as well. So that could be one way of confirming if there is a planet out there. Of course, if we don't, then it could be a black hole, So there's a couple of different ways we could test that as well. The Roman telescope that's coming soon, the Large Synoptic Sky Survey telescope, might be able to do that as well. There might be some Hawking radiation from the black hole that maybe we could detect as well. So a couple of different ways. But I think the James Webb Space Telescope is definitely the thing that everyone's hopes are riding for on this, along with many other people in science as well, right? I feel like there's a lot of areas of astrophysics that are currently their hopes are riding on the James Webb Space Telescope.
So I could probably Google this, but when is it being finally put into operation? And
October 2021 is the launch. And obviously that's been pushed back. So I remember starting my PhD back in 2013 and it being 2017, and that's sounding so far away. And that's been pushed back and pushed back. It was March 2020 at one point. We all know that was never going to happen, did we? But now it's actually going through the final testings before it actually gets shipped to French Guiana, to the launch site. So that date of October 2021, it actually has a day now. It's the 31st of October 2021. So the fact that it has a date tells you, they've got their little project management schedule, and that looks very, very likely that will hit it now. So it's going to be a very nerve-wracking day when that gets launched, and it's going to be a very nerve-wracking couple of weeks as it travels out to 150 million kilometers away from the Earth and then starts to fold out. We check that everything is still working as we expect. I'm in great awe of a lot of the science teams at ESA and the Canadian Space Agency and NASA as well that are working on that. They're doing a fab job.
Yeah, and I'm presumably trying to get time on that telescope to point at the thing you wanted to point at is going to be a huge battle in the astrophysics community. Yeah,
it is. They've already actually opened sort of applications to say, what would you want to do with this in the first sort of phase of James Webb being operational. So that's how you knew it was real as well, right? Because they started asking for proposals of what you do with it. But I think a lot of people realized that it was going to be very oversubscribed, and there's a lot of people working on similar things that sort of banded together and put in a big sort of collaboration of people that would like to, to look and agree on something. So I think it's going to be very collaborative, because we know that unlike Hubble, which has been going for 30 odd years, right? Because we could service it and, you know, give it more fuel. Webb is got a set lifetime, and when it runs out of fuel, that's it. You know, it'll start to decay in its orbit, and it'll start probably to fall into the sun and die a fiery death in 5 to 7 to 10 years or something. So we know there's limited lifetime, and people are very aware that they're like, okay, this is what we want to do with this thing. Let's get on with it.
Well, it's very, very exciting time to be an astrophysicist, I guess.
It is, yeah.
So now
it always is.
something a little bit different. We've got a few questions about quasars. So somebody asked, are they actually useful for anything? So like acting like a standard candle or clock, so that you've got a regular pulse that's kind of coming at you. Is that useful for anything?
So quasars don't tend to have like a regular pulse or anything like that. Some of them do have these big jets that come from them as well. So the jets don't come from the black hole. Again, they come from the region around it. You're essentially putting in material far too fast, and the pressure around it grows and grows and grows. And you've also probably got magnetic fields, and if you've got the hydrogen gas is probably a plasma rather than like a gas, so you've got charged particles moving around, and all that sort of starts to get funneled up by these magnetic fields into these big jets that move at close to the speed of light. And we can detect those, but they don't pulse in the same way that like pulsars do, with their sort of magnetic field radio waves that come at you at, you know, incredibly high rates. So, you know, some pulsars, they're millisecond rates, right, that we detect of these little lighthouse pulses. These jets are more aligned to the galaxy disk, because it's coming from the material around the black hole, not the black hole itself, right? So they don't tend to move in any way or pulse in any way. But yes, quasars are very, very useful. We can get distances to them. So a lot of the most distant objects we've ever observed are actually quasars as well, because they're so bright, and that helps us put a distance on other things nearby as well, so we can get some sort of idea of distance. They're not a standard candle necessarily, because the brightness of them depends on the mass of the black hole. So you've got to measure the mass of the black hole to know how bright they would be, and that's not always possible. But they are very, very useful things. We actually now, I said when they were first spotted, these quasi-stellar objects, they couldn't see the light from the stars behind them. But now with our better telescopes that can see fainter things, we can see the light from those stars. So getting a redshift, and therefore a distance to that quasar, then tells us how old that galaxy is. Obviously, we're seeing it as it was when the light left us. So they're enabling us to sort of like piece together you know, the evolution of the universe a little bit as well, but just by giving us more accurate distances. Also, the light from quasars, because it's so bright, actually passes through, you know, a lot of hydrogen gas on its way to us, and the hydrogen gas will absorb a little bit of that light, and you'll end up with sort of a gap at a certain wavelength, and that can tell you about sort of the distribution of hydrogen in the universe as well, which is really exciting stuff. And there's a lot of people that do that, and again, that can tell us about how the universe has evolved. So quasars, cool objects and very useful. So
fantastic. I've just gone back into the chat, and there's just been like a whole bunch more questions.
I'm
So I'm
sure,
going to try and get through as many as I can. So I think I actually answered my follow-up question about why quasars emit so much energy, because they're being pulled together, but then those jets, like you say, are coming out because of the pressure. So I think we answered that one. What else have we got? So there's been a few people mentioning white holes, which I think are sort of theoretical objects. People say, what happens if a white hole and a black hole merged, and and all these kind of fantastical ideas. So I don't know if you wanted to say a little bit about them. I think they're theoretical at the moment. I don't think we've seen.
Yeah, no, we haven't seen a white hole. I think we'd know if we'd seen a white hole. So a white hole, you know, you can sort of, if we think about it in the terms of Einstein's theory of general relativity, right, where space-time is this fabric, this sheet, that if you put a big heavy object on, it will sort of depress that sheet, and that's the effect of gravity, right? And the idea of a black hole is that you get to a point where the only direction is towards the black hole. A white hole is, I think it might theoretically be like a solution to the general relativity equations. I'm not entirely sure on that. But essentially for a white hole, it's the opposite. Like the only direction material can go is out, or energy can go, or light can go, or something like that. So these would be the brightest objects in the entire universe, right? And we would have spotted them, I think, if they actually existed. I also like to throw in here as well the idea of a wormhole. That's something that's not as well understood by people, I think, because sci-fi probably has a lot to answer for. But a wormhole is not a black hole. So you often hear people being like, oh, well, if you could travel into a black hole and it'd be a wormhole to somewhere else in the universe. That's not what a wormhole is, right? So people think of them as being like a black hole on one side and a white hole on the other side. But wormhole is a solution to Einstein's equations to describe this curved sheet, right? It just, they don't have this event horizon. I almost like to think of them as like a wormhole is two funnels back to back, whereas a black hole is a funnel with the end pinched. There's just nowhere to go, right? So with a wormhole, you will always be able to escape it. You have to be able to escape it because you have to be able to travel in and out of it, right? They're just sort of like, if you could bend that fabric of space-time and join it up somewhere, that would be what a wormhole is. Again, completely hypothetical, but used a lot in sci-fi as plot moving on points, right? And I think there's a lot of misconceptions over wormholes, white holes, black holes, out there. So I hope I've cleared that up a little bit for people.
Well, that's fantastic. There's been a few questions about this idea of rogue black holes, which I have to say I'm quite taken with as well. So Natalie says, are there any traveling black holes that travel around? And Chunlang Mu says, can there be rogue supermassive black hole with no host galaxy? And if there is, can we detect it?
In theory, yes to all those questions. So you can imagine you have these big star clusters that form. So lots and lots of stars formed where hydrogen was quite dense in the universe, right? So you end up with them in these big clumps, right? So then you can get lots of those stars going supernova and black holes forming. And then all of a sudden that would probably disrupt some of the orbits around them a little bit. And then you could have sort of things slingshotting around each other gravitationally. And then you could fling out a black hole into interstellar space and you'd end up with a rogue black hole. Similarly, in a supernova as well, we've seen neutron stars being flung out instead of sort of staying in the middle of this big supernova where everything's being, where the hydrogen gas on the outside ricochets off into these big, beautiful nebula. The neutron star ends up being pinged out. And we've actually seen that happening. That is a real object. I can't remember the name of it off the top of my head. So there's no reason, that couldn't happen with a black hole as well. I suppose with supermassive black holes, yes, there definitely could be those as well, because in the merger of two galaxies, you could get the same thing. Instead of them merging together, they could be on just the right trajectory and orbits to come slingshotting around each other and shot out into intergalactic space as well, right? I don't think we've ever found that, but we have found two black holes sort of sloshing around each other, and we found a single black hole also not in the center of its galaxy as well, sort of sloshing around. So again, there's no way of knowing whether that's sort of about to slosh into the middle or if it's about to be chucked out into intergalactic space and become a rogue black hole with no galaxy. But theoretically, yes, that would be possible.
And just on that, do we know what is in intergalactic? Is there anything in intergalactic space? Have we found any sort of rogue stars that have got lost, or bits of thing? I mean, I know it's very far away and be very small, and space is very big, but
yeah, in our own Milky Way galaxy of sort of intergalactic space between, say, like us and Andromeda or something, there are sort of like the corpses of little galaxies that have been stretched out into these big sort of streams that go around the Milky Way. So I guess you could say that's an intergalactic space. But most of the intergalactic space, we talk about space as a vacuum, but you're going to happen upon a little particle of something eventually. It's just that it's a lot less dense, right? It's very unevenly distributed, all the hydrogen, right? You've got a lot of it clumped up in stars, and then in between it, you've just got very diffuse, like lots of little clumps of hydrogen. You've also got a lot of dark matter out there as well, we think. Even in the solar system, we think that there is a proton's worth of mass of dark matter in every teaspoon of space. Even here, pick a teaspoon cube of space, and you'd be like, there is a proton's worth of dark matter in that, we think. So again, it's very diffuse in comparison to like how compressed it is in stars, but it's still there. So it's just this very, very underdense sea of hydrogen and dark matter, I think you can think of it as. And maybe the odd rogue supermassive black hole, we hope.
And the odd starship just cruising to another galaxy or something.
Who knows? It's a very long journey.
So Connor asked a question, going back to the dark matter, dark energy. Presumably, as I know you said they're not hoovers, but as matter is sort of orbiting black holes and going into that, would also include dark matter, right? And do we think dark matter could be adding to black holes, and how would you think they would interact?
So I had this exact same question while I was writing up my thesis, and I thought this was like my eureka moment. And I was like, oh, I've cracked everything. Like, this is how stuff grows this big, because there's dark matter that we've not thought about as well. And I went like running down the hall to my colleague being like, has anyone thought of this before? And they were like, I don't know. You'd have to check with the people who simulate this stuff. Do they include dark matter? And I went to talk to a lot of simulation friends, but in the end, it turned out, yes, probably a little bit, but not as much as you think. And it's also incredibly difficult to simulate as well. So there is going to be dark matter around black holes, but it's getting it from the orbit into the black hole itself is the big problem. And it's actually harder to do that with dark matter than it is to do that with normal matter, because dark matter is something we call collisionless. So when we've seen like big clusters of galaxies merging together and we've been able to track where the mass has gone, we see that dark matter has just sort of passed through each other completely undisturbed, because it's very unlikely to collide with another dark matter particle. Unlike, if you think about a big gas of hydrogen with lots of energy, with all these particles pinging around the place, they're going to be pinging off each other like cue balls on a pool table, on a snooker table, right? That's what makes them lose energy from this sort of orbiting around the black hole and this, what we call the accretion disk, the material that the galaxy will eat, the stuff that glows so that we can see it. There's lots of collisions taking place in that. And eventually particles will lose energy in those collisions and eventually fall into the black hole. If there's dark matter in that disk, it's very, very unlikely to collide with another dark matter particle. And so they're very unlikely to ever lose energy. And therefore, they're very unlikely to ever fall into the black hole or become part of the black hole's mass, as we said before. We should say what it's called to challenge the misconception of a hole, right? So unless this dark matter is maybe falling in as part of maybe, again, one of these little galaxies that's coming in, bringing some dark matter with it, and it's on a direct trajectory with the black hole, it's unlikely to contribute to the black hole's mass. My simulation friends apparently estimate it to be around about 10% of all the stuff in black holes is probably dark matter, but that's probably an upper limit. It's probably less than that, just because of this unlikeliness that the dark matter will ever lose energy to be able to fall into the black hole.
Fantastic. So David Howes has been asking a few questions that I confess I don't quite understand, but it seems like it's important.
I'll have a crack.
So he's talking about the ergospheres of black holes, and how do you account for them when you're measuring the difference in light frequency caused by special relativity? Now, you'll have to try and explain to me what the ergosphere of a black hole is, and how.
I don't think that that's actually relevant here. I don't account for it in my research anyway, so
yeah.
Trying to think if that's.
No,
you've puzzled me there with that one. Leave it with
me. So what was I going to say? When we talk about black holes, though, there are these different sort of defined points around it. So we have the event horizon, we have the ergosphere, we have the Schwarzschild radius,
which tends to be classified as the event horizon. Yeah.
Could you just explain a little bit about what those are and how they relate to the size of the black hole?
Yeah. So the Schwarzschild radius is the event horizon of a Schwarzschild black hole. I know I'm pronouncing Schwarzschild wrong. I apologize to all the German speakers out there. I've been told many a time and I can't get it. That is the event horizon of what's called a Schwarzschild black hole. So under the assumptions that Schwarzschild made to solve Einstein's theory of general relativity for the instance where you have everything crushed down into an infinite point, so that you have this infinite density, that's the radius you get, at which point you would have to be traveling at the speed of light to escape the gravitational pull. So that's the event horizon, the Schwarzschild radius. That was the number I showed on the slides as well for my iPhone mass black hole, right? That's what it was. So, those are the regions around it that we have, and you'll hear people refer to lots of different things. You also have something that's called the ISCO, the innermost stable circular orbit around a black hole. That's used a lot by people who simulate black holes as well, to know at which point, it's not necessarily the event horizon actually that you would be sort of lost forever. So if you have this accretion disk around the black hole, all these collisions happening where material is slowly making its way in onto smaller and smaller orbits, the innermost stable circular orbit is the last point that you can have something orbiting it before it will just chaotically spiral in and at some point cross the event horizon and become part of its mass. But the ISCO is a lot bigger than the event horizon usually. So I guess at that point, when you've crossed the ISCO, then's when you can think about black holes as hoovers.
There's an interesting question here from Ian. This is about the end of the universe. So just before you answer, we had a great talk about a year ago. Oh no, about last August, I think it was, from another fantastic astronomer, Katie Mack, who I'm sure you know. Yes,
love Katie. And she came to Oxford like before the pandemic, and we went for ice cream and had a great chat. And
Yes, she's delightful. And she wrote her book last year was about it's called The End of Everything. It was about
that's why she was in Oxford. She was doing like research for the book, and she was chatting to a lot of my colleagues, myself, and I was just like, "Can we do it over ice cream?" So we went for ice cream.
Anyway, so Ian asked, I remember being told that one of the stages during the end of the universe is that black holes will evaporate. Can you explain this? What will happen to black holes when the universe finally dies a miserable heat death?
So evaporation of black holes is to do with this Hawking radiation that Stephen Hawking came up with. So the idea is, and I will confess that I do not fully understand Hawking radiation. It's part of quantum physics, and I don't think there's anyone out there who would ever claim to understand quantum physics fully, because it is just one of those weird and wonderful things. But the idea of the Hawking radiation is that at the event horizon of the black hole, you could spontaneously, out of the energy that is in the vacuum of space, create a matter particle and an antimatter particle that would reduce the mass of the black hole. Like the energy would come from reducing the mass of the black hole. One of those particles would fall back into the black hole, and one of them would escape. And that escaping particle would take away energy from the black hole. But that is a spontaneous thing that happens out of quantum mechanics that's highly, highly unlikely. But according to Stephen Hawking, if you do the maths, it is possible. It's never something we've observed, so it's still hypothetical. But in theory, that would mean a black hole could evaporate. Like it could lose all of its mass and get smaller and shrink by these particles in this Hawking radiation taking away energy or mass from the black hole. Einstein, E equals mc squared, energy and mass are equivalent, right? So in theory, that could happen. However, because it is so unlikely, it takes a really, really long time. So for example, supermassive black holes, I don't even know the number because it's such a stupidly large number, but it would be longer than the age of the universe, like orders of magnitude, like 10, 100, 1,000, tens of thousand times longer than the age of the universe for a supermassive black hole to evaporate. So the universe has only been around for about 14 billion years. Even, primordial black holes, which are these much smaller black holes, like the one that may be in the solar system that's about grapefruit sized, even that, the universe has not been around long enough for that to have even had enough time to scratch the surface of evaporation. Of course, if we're thinking about the end of the universe and time going on forever, then maybe, yes, if you wait long enough, eventually space will expand. The space between galaxies will become so large that you can't even see galaxies anymore. Stars all start to die off and go supernova, and no new ones are formed. And you just end up with lots of dead things like neutron stars and white dwarfs and black holes that then all start evaporating, and you just get left with nothing, right? That could be. But that is so many trillions of years in the future that there are probably far more likely things that could happen for the end of the universe before that than that would ever happen.
So someone asked a
Cheerful
question.
Subject.
Oh, it's a well. Luckily, I'll be long gone. I don't need to worry. Someone asked a question earlier in the chat. Yasir Rashid, I've just found it. And I thought they were being like slightly flippant and silly, but actually it's a really interesting question. So I apologize for thinking your question was silly. Yasir said, do black holes have hair? And I thought, well, what kind of a question is that? Turns out it's actually a very interesting problem in black hole physics. So I don't know if you want to say a bit more about what hair is.
I don't think anyone really knows what hair is. That's the problem. Again, it's one of these sort of odd things about black holes. So there's all these things about the no hair theorem and the hair theorem. Again, this is so theoretical that I don't know whether there's anything observational that we could ever make to prove that this was the case. So there's a couple of different things, like there's properties of the black hole that are measurable, right? There's the mass of the black hole, and some would argue you could also measure the spin of a black hole. So like, the Earth is rotating, the sun is rotating. As stars go supernova, they still have this energy from their rotation that gets imparted to whatever's left behind. So the black holes are also spinning as well. And so those were the sort of the two things that were like the properties of the black hole that you could measure. But there's this thing now, it talks about hair on a black hole, that would be, tendrils, for want of a better word. It's a very, very complicated thing. And I will be honest, I don't think I actually fully understand it yet. What I care about is being like, okay, theorists, you decide whether it's the no hair or the hair theorem, and you tell us a way that I can then go use my telescope to prove either way, one or the other, which one it is. That's sort of my role as an astrophysicist, and I'm very, very happy in that role. I'm very happy to let the theorists sort of like scribble away on their blackboards and simulate away things in a computer as well, and then just come out of the little hole and say, it's this one, and then go back into their hole. So
and actually, just to lead on from that, is a question from Roy Simpson, who says, is it possible to measure whether the central black hole is spinning? And if it is spinning, how do we measure that? How do we know?
Yeah. So I'm currently trying to do this as part of my research, because the idea is if you're feeding the black hole from inside one of these bulgeless galaxies, these egg white omelets, then all the gas is coming from the same what we call angular momentum vector. It's all coming from the same direction. So you're going to spin up the black hole. So we'd like to measure if they have higher spins or not. So there are many people who say this is possible. And there are many people who say this isn't possible. And it's a big point of contention in the literature. If you ever dive into astrophysics papers on this topic, you'll see there's sort of cat fights happening very politely. But there is a way you can do this if you look at the X-ray light of the black hole. So the X-ray light will have this sort of like distribution of how much light of each wavelength you're getting. And depending, it will peak at some point, and depending on where that peak is, you can tell where the innermost stable circular orbit is, which also depends on the spin of the black hole, and therefore you can get at the spin. But there's so many different assumptions that go into that, and there's so many different what we call degeneracies, where it could be one thing, but it actually could be another thing that's affecting it. And so you're trying to derive one thing, but actually it might be this thing. So it's very, very difficult. And that's why people argue that, we don't have good enough data to do this, or we don't have good enough models to do this. And there are some people that say, no, you can do it as long as you're happy with making all of these sort of brush under the rug assumptions. So that is one way we could do it. Because there's a lot of people arguing about whether this is possible, we've decided to again go to our little simulation friends and say, okay, they're not little, but you know what I mean? My little simulation friends, make them sound like some sort of like minions or something, don't I? I go to them and say, you simulate the gas that comes into black holes, you simulate the vector it comes in, you know what spin they're coming in at. So if you look at galaxies that haven't had mergers, what do you find? And if we can at least test the hypothesis there that we have that these bulgeless galaxies should have higher spins, that's at least one test, while that sort of observational debate about whether it's possible to measure it with your telescope sort of rages on, and maybe in a decade or so they settle on an answer of whether it's possible or not. So a good question.
Yeah. So we're sort of coming towards the end here, but I'll try and throw you a few more questions before we wrap up. Shivam asks, what is your theory of everything? If you had to put a bet, or what's your favorite theory? What do you have anything that concerns you? Or given that you only really deal with things on a gigantic astronomical scale, a general relativity scale, are you sort of not that fussed about tying together the nuclear forces?
Yeah, I feel like particle physicists are more fussed about tying that together, and us astrophysicists are being like, we got general relativity, it's pretty good. We told you to figure out dark matter ages ago. Like, come on, what's taking you so long? I think I would definitely like to know what dark matter is in my lifetime. That would be great if either it turns out to be a particle physics thing or an astrophysics thing, whatever it might be. I think the theory of everything I'd like to see is I would like to see general relativity tied into like a quantum theory. Like if we could link the sort of quantum scale and the astrophysics scale with a theory that describes all of that, that would be great. That would be really cool. But as you say, like I'm bothered about the much larger scales that we, general relativity has worked great so far, and it's even led us to this idea that this dark matter is out there in so many different places in so many different ways. So I'm kind of happy that we do have that, and I think once we understand dark matter better, I'll be a lot happier, because then we'll be like, okay, so general relativity is right because all this dark matter exists and it's made of this as well, and we understand that now. So I think that's what I'd like to see more than anything.
I'll email my theorist friends and pass on your comments. Drew, that's an interesting question, which is not something we've mentioned at all yet, which is this idea of information going into a black hole.
Yeah.
And I think that might be, I feel like there's something there, isn't there? Some kind of paradox or something. What happens to information as it goes into a black hole? And is it destroyed? And does that violate all kinds of laws of nature?
That's the thing. The information paradox was huge, right? The idea that like information and like information is technically energy, right? Can't be created or destroyed. Like, is information technically lost when it falls into a black hole because you can't get it out again? I sort of get my head around this as like being like, it's just part of the black hole now. Like, yeah, okay, we can't see it. That doesn't mean it doesn't exist anymore. It's just part and parcel of this object that now exists that's quite exotic, but it's just, the Raichu to neutron stars Pikachu's. It's just a more exotic form of it. And I feel like that paradox would probably be resolved if we could understand better like what a black hole was made of, if anything, if it is some exotic form of matter, or if it actually is described as a singularity. And I think that's where the issue comes in with this information paradox. But I think it is, it's just, energy is not created, it's not destroyed, it just is part of the black hole now, and it will forever be part of that black hole.
So just to wrap up, a lot of people commenting 42 in the chat. So well done to all the hoopy fruits who are celebrating.
Yeah, I should have mentioned 42.
Just a couple.
Should have had a towel. Should have done the very American thing of like
waving a towel
around our heads.
So just a couple of more sort of general fun questions just to finish
on.
So Derek says, what discovery in the field would surprise you the most? Obviously, like, there being a giant panda that floats around the sun or something would be surprising, but like within the bounds of possibility, what do you think would be a kind of very surprising result that maybe the James Webb would give us?
I don't know about the James Webb, but I think it would really surprise me if dark matter doesn't turn out to be a particle physics problem. Because particle physics have this standard model that describes all the particles in physics. And if it turns out that, dark matter can be described by some extra addition to the standard model, supersymmetry or whatever it might be, sort of that you hear about, if it didn't turn out to be that and it turned out to be something astrophysical. So we've thought about before, could lots and lots of tiny black holes explain dark matter? Could it just be all of the dust and gas and brown dwarfs and white dwarfs of neutron stars that we can't really see in the universe? Like, could that be dark matter? And we've ruled that out at so many different stages in so many different ways, by simulations, by observations, and we've ruled that out. But there's still this thing where it could be something else astrophysical that we've never observed before. And I think that would be what would massively surprise me, is that we've ruled out all the things that we do know, but it could be something that we don't know yet, at least, right? And I think that would surprise me the most.
So S. McNeil was asking if you read any Larry Niven when you were younger, and more generally, I think somebody else asked, were there any other books that kind of inspired you when you were young, and what books would you recommend for astrophysicists or budding young astrophysicists?
I had a space book that was I think it was by Robin Scargill, because I looked it up a while ago and I found it, and it was beautifully illustrated. It had like a fact file for all the planets, and it was stars and galaxies and black holes. And I do vividly remember the page on black holes, and it was the first page that didn't really have an image, because back then we didn't have an image of a black hole, and it was all artist impressions. And I remember being like sort of resigning myself to there never being an image of a black hole, like being fascinated by them and wanting to know so much more, but resigning myself to there never being an image. And that's why I'm so in love with the big orange donut image that the Event Horizon telescope took. So that definitely inspired me as a kid. I was also I wanted a telescope rather than a bike. I was a why child. I constantly asked my parents and teachers questions. It probably drove them mad. I think now, there are great books out there that are written not necessarily with kids in mind, but I think we underestimate kids quite a lot on what they can take in. And I think if your kid is interested, like, yes, a book that about space that it is heavily illustrated, but necessarily does have a lot of information in it, like they'll devour that, whether it might be, now where they'll fully appreciate it in a couple of years, it'll keep the interest growing. And there are kids out there that are interested, like astronomy societies, right? Like there's loads of local astronomy societies that you can get involved with, and you'll surprise you. You probably have a quick Google, see if there's one in your area. Because I know telescopes aren't accessible to everybody, because of price points, but astronomy societies, they'll turn up with telescopes, plunk them down on the ground, and everyone just has a bit of fun for an hour stargazing somewhere local to you. So and they also have talks like this as well that they run. And that's a great way to sort of keep up your interest in science. Another way is the Zooniverse, which is a citizen science website which I do a lot of my research, or a lot of my research is made possible by. So I use a site called Galaxy Zoo, where we uploaded the images that were taken by Galaxy Survey, over 1 million of them. 1 million is far too many for astronomers to classify, at least 15 years ago, before machine learning really took off. Still is now, to be honest, because machine learning is not very good at this kind of image recognition when there's so much variation. But a human can be like, that's a spiral, that's a blobby elliptical, that has 3 spiral arms, that doesn't, that has 2, you know? So it's one of those websites where you can contribute to real science that's happening that couldn't happen if it wasn't for the power of the crowd coming together to classify these huge, huge data sets. And there's everything from astronomy on what is now, you know, Galaxy Zoo is under the Zooniverse. There's everything from astronomy to history to ecology to penguinology. I love the Penguin Project, you know, trying to work out how overfishing is affecting penguin colonies and stuff, from people being like, there's a penguin there, there's a penguin there, there's a penguin there, there's a penguin there. It's fantastic. It's such a great way to get involved in science and know that, you know, maybe something you do on your commute, instead of playing maybe like a game like Angry Birds or something, like you can, a couple of clicks can contribute to world class, like, you know, on the edge of knowledge science. So
yeah, I just want to give my own personal shout out to Zooniverse and also is it Chris Lintott, who I think was your supervisor?
Yes, he was my PhD supervisor. Yes,
and people in the UK might know him. He's often on the Sky at Night and various other places, but he's kind of the one of the major forces behind that site, and yeah, all power to him, basically, because it's a fantastic resource. I think actually, I don't know if we actually did it. I think we were going to put some old Humphrey Davy notebooks on there, because he has terrible handwriting. So we do need some actual humans to try and decipher what he was on about. So yeah, it's a great platform that all kinds of science and history research can take place on. So yeah, I definitely recommend you Google that. Just finally, before we go, sorry, you can say something.
I was going to say Zooniverse is a funny word, so I was going to spell it. It's just Zooniverse.
Yes, I should have done that well. Thanks. So just finally, Jack asks, Dr. Becky, what is your favourite star and thing in space?
Favourite star? I don't know if I have a favourite star. I think if I had to say anything, I'd probably say Betelgeuse, because I remember a vivid memory of me asking my parents like why that star looked a different colour than the rest of them around it. It looks reddish because it's a red giant. It's about to go supernova any day, which could be in the next 500 years, any day. So I guess I'd probably say Betelgeuse. My favourite object, if it couldn't be a black hole, it would, and anybody who follows me on YouTube is going to know exactly what I'm about to say, but it would be Saturn, because I think Saturn is the coolest planet ever. And I won't hear any other answer for the best planet in the solar system. Saturn has everything. It has the rings. It has a hexagonal shaped storm at its pole that's just raging around its storm, but in a hexagon shape because of standing waves, which is just physics amazingness. It has some really cool moons as well that could be the best places to find life elsewhere in our solar system as well. And it just looks so beautiful. I'm just like, how could you not love Saturn? And the fact that you can see it with your own eyes as well. A decent enough telescope, you can see Saturn's rings. And the fact that, you know, you can see that with your own eyes is just fantastic to me. So that's why it's my favorite.
Yeah, I mean, I was watching one of your videos the other day and I was blown away by this hexagon on the top. I feel like, why has nobody told me about this before? That's amazing.
Yeah, well, we could give a whole other talk about the hexagon on top of Saturn, so gladly.
Well, maybe next time. Unfortunately, we're actually slightly over time, so thanks to everyone for sticking with us. Thank you so much for all your amazing questions in the chat. It's been very lively. I've been trying to pull out as many as I can, so sorry if I didn't manage to get around to asking your question. Just a quick reminder to everyone out there, anyone in the world is welcome to join the Royal Institution as a member or a patron. There's no qualification, nomination, anything like that. You just need to like science and want to support our work, and you can become a member, like me and Einstein and David Attenborough and many other great people. So you can do that. And as I say, if you've already made a donation towards this talk, we really appreciate it. If you haven't, but have now considering your life choices, please go to our Just Giving page and drop us some money. We would be hugely appreciative of it. We are a charity, and we would just be grateful for any contribution you can make. Don't forget, we'll be sending out a survey afterwards, and also don't forget that we've got Chiara Miletto on Thursday talking all about counterfactuals. So that should be a really interesting philosophical and physics talk, alongside, of course, 2006 Christmas lecturer Marcus de Soto. God, it's a real Oxford week. Just everyone's from Oxford this week. Well, you know. Well, it is.
We're everywhere.
It is Britain's second best university, so that is good.
What? Because Durham's the first.
Anyway, we'll not get into Oxbridge squabbling, but just before we go, Dr. Becky, I'm sure lots of people will know you from YouTube and other places, but just can you give us sort of a list of where people can find you if they want to find out more or get in touch?
Yeah, of course. So I'm Dr. Becky on YouTube, but also I have different social medias. So Twitter at Dr. Becky with an underscore. On Instagram, it's Dr. Becky _S. I think I'm on TikTok now as well as Dr. Becky, so you can find me there. We'll see how that goes. And also you can find my book. It's called Space, 10 Things You Should Know in the UK and World Markets. But if you're in the US and Canada, it's called Space at the Speed of Light.
Fantastic. Well, thank you so much, Becky. I've had a tremendously fun evening and just learned an absolute ton. So thank you so much for spending the last 90 minutes with us. And thank you all for watching. Good night.